everyone. My name is Evelyn. Today I'm going to be talking about the field of paleoclimate. So, a little history first. Paleoclimate was heavily reliant on the development of its daughter fields. So, consistent weather tracking was needed, the buildup of our fossil record was needed, as well as technology advancements in chemical analysis. So many fields are used to patchwork evidence of what is the ancient climate of Earth. Fields like meteorology, geology, biology, technology, um, they were all necessary in development before paleoclimate could exist. So, booming now in the 20th century, there is a much greater need for paleoclimate research because of human induced climate crisis. We analyze conditions that mimic or resemble the climate predictions for the future, which is a perfect reference for developing a plan for remediation. Initially, at the turn of the century, the findings in paleo studies were faced with turmoil from the public. Many refused to accept overall presence of climatic changes, and most of them refused to even accept that it was human caused. Malcolm K. Hughes was a really influential scientist in the climate studies battle. His hockey stick graph really visualized the rapid global warming and turned the public's eye and really conveyed the urgency of the planet's state. First, I just want to differentiate between climate and weather. Climate is the statistical trend of weather over a large region in a long period of time, whereas weather describes only day-to-day fluctuations. And so when talking about paleoclimate, it is the ancient climate patterns of Earth. Here's a really great visual from a study published in 2014. This graph was made by compiling data analyses of many proxies from many authors over time to estimate the temperature of Earth over the last 500 million years. And so many aspects of this graph reveals clues about the past, like glaciation events. You could see last glacial maximum right here. It also reveals the difference between long-term and short-term climate variation. You can see in the Pleistocene there's large changes up and down, however, not a overall trend difference. And so it's fair to say a colder than average month can exist within a long-term warming trend, and that's what paleoscientists really aim to do with this giant conglomeration of a graph. It's to show that overall there's a lot of data, but combined, the trend is apparent. Oceans and climate are very tightly connected. Before I talk about how paleoscience scientists study and gather evidence to deduce conclusions about ancient climate, it's important to understand how our climate even changes on its own and why it changes. As plate tectonics has changed over time, so has our oceans. And oceans are the most influential on our climate because they store and transport the sun's energy as well as absorb and release CO2 from the atmosphere. And so water's chemicals properties, the oceans can absorb much more of the sun's energy than land can, while also redistributing the heat by its currents. So as the currents have changed, like I said, because of plate tectonics, also has the heat distribution. Oceans also have a thermocline in them, which separates the warmer surface water from the cooler, dense, deeper water, and that can be from anywhere between 200 to 1,000 meters. And the thermocline is especially important when talking about climate because the cool layers of the oceans are able to store carbon dioxide and other minerals, which is a form of sequestration essential in the carbon cycle. Here's a great visualization of the hypothesized Eocene plate arrangement about 50 million years ago. You can see that there's a really large equatorial current, one that is directly responsible for the higher global temperatures characteristic of that epoch, much different from today's global ocean currents. More These are more vertical, whereas this is horizontal. This current right here on the equator was able to absorb most sunlight that is now being reflected on the equator. And so that fact alone and the heat distribution of the fluid caused massive warming periods on a very simplified scale. And it's very oversimplified while I'm describing it, but just to get the gist. So yes, that's just one reason why climate varies. Another reason why climate varies is because of Milankovitch cycles, which have been just only recently understood. Milutin Milankovitch, who did most of his work in the early 1900s, is a Serbian scientist and mathematician who did revolutionary work. He really deduced all the ambiguous patterns of glaciations and such. And to put it in a brief way, there's much more complicatedness that goes into this, but Earth's tilt and rotation and orbit around the sun varies directly with its temperature. And the Milankovitch cycles talks about the slight variation in Earth's orbit caused by gravitational effects of Saturn and Jupiter, which happens every 405,000 years. The Earth to sun distance changes. And with that change, the temperature directly correlates. Another reason why glaciation events occur in a cyclic way, and why climate changes overall too. And so to get into how paleoclimatologists use climate proxies for different data, they choose their proxies based on the time span they need to cover. So ice cores can cover a limited amount of time in history. So can tree rings, a little bit less than ice cores. Ocean sediments can cover most of history. So depending on what you're analyzing and what you're looking for, you have to choose different proxies, and they all have different resolutions too. So some proxies that they use are tree rings and coral rings. They form in layers, so it's easy to determine the timing of the formation of those layers and the isotopes within them. Sediment cores and ice cores are similar, and they're also used in the same ways. They're dredged up, and their layers are able to show scientists a really distinct timeline, and they look at isotopes in those as well, and fossils in those as well as gases, trapped gases, and water. So starting with ice cores, they're a very important tool since they come from areas like the poles that are very well preserved and undisturbed throughout time. Ice cores have distinct layers, and those and the thickness of those indicate the rainfall of the time. And so ice cores can be broken up by scientists, put in a vacuum, melted, and the gases that are trapped inside, or organic materials that are trapped inside, can be isolated and tested. Sediment cores are similar. They kind of accomplish the same sort of task, looking to analyze the layers going back in time for fossils and organic material to be isotope tested. Scientists are able to create a timeline because of the sediment layers stacked on top of each other. There are also measurements done with sediment cores that are able to reveal the rise and the fall of the sea level over time. So radiometric dating is crucial for climate science, for paleoclimate science studies, because it uses all organic, all or mostly organic evidence, which is really great when looking at the paleo evidence that is needed. So radiometric dating evolves using the universe's naturally occurring radioactive elements, which are inherently unstable because of their unusual neutron numbers. So carbon and oxygen are organic, and they can either have more or less neutrons in their nucleus, depending on the sample. And a radioactive element has a half-life, and scientists use the half-life in a sample to determine the age of the organic material. And if there is an interesting specimen with no way to date the organic material, they use bracketing techniques dating organic material either in the carbon form if it's less than 50,000 years old, or in the igneous form if it's greater than 50,000 years old. They use bracketing by determining the age of layers around an interesting artifact, to say it's between a certain amount of ages. Uranium and potassium are used in igneous rocks because they have a longer half-life than carbon does. However, it's just a much less precise way of measuring the date of a sample, which is why it's not used as it's not a very prevalent form of evidence. So oxygen 18 can also be in isotopic form as well compared to its normal oxygen 16, and it's used when analyzing water inside of materials. So it's used in ice cores and also anything else with water inside of it. Oxygen 18 is heavier than oxygen 16, making it always consistently condense readily and fall faster when it's raining when compared to the lighter component, oxygen 16. So the ratio of these two isotopes in a sample tells scientists about the temperature and the precipitation of an area, because the warm water evaporates the lighter isotopes quicker. Benthic forms are found in sediment cores and are analyzed with isotopes too. And they're also called foramina. It's a cute word. Um, They have an extensive fossil history, though. They've been around for more than 66 million years and always abundant in the marine sediments. And so their calcium carbonate shells are the perfect material to analyze isotopes from because they have both oxygen and carbon. And scientists are able to get long-term temperature data from them. Corals are, like I said, banded in the same way that trees are, but their skeletons provide climate data about the sea surface temperatures and the sea surface salinity, either through their oxygen isotopes or the strontium to calcium ratios in their skeletons. On this slide, it says carbon to calcium. It should say strontium to calcium. Sorry about that. So just from those isotope ratios, paleoscientists can determine the balance of precipitation to evaporation or terrestrial runoff or continental ice melt and ocean circulation, all from different forms of evidence. And there's many more proxies that they use that I just haven't mentioned. These are just the main ones. Tree cores, very important, also called dendrochronology. It interprets the past events based on tree rings. So samples are obtained by a borer, a simple metal tube, and it goes right into the bark, and the rings are sequenced with other cores from other trees and kind of made into a big long procession. And so it's all based on the fact that many species of trees produce growth rings during the annual growing seasons, and the width of those rings um, correlate to the various external factors that the plant was put through, like temperature and precipitation, and all the overlapping rings can give scientists enough evidence to